Hi everyone, am I audible? Is the mic working? Good. So, welcome to this lecture on transformers and graph neural networks. The slides are going to be up in a minute. I think somebody is getting the connector, USB-C connector. And if they don't have it, then I'll borrow one of your laptops, if that's okay. But yeah, we're doing this lecture for the first time in the course. Transformers and graph neural networks has never been covered in the course, so you're part of history today. And I'm not Bhiksha, I am Akshat, and I'm going to be teaching this lecture today. So a little bit about me. I just graduated from CMU last semester, spring 2021. I was doing my master's in ECE here, and I've been involved with this course the 3 semesters I was here. The first semester I took this course, then I TA'd it for the next 2 semesters. And I mean, glad to be back again. And it's an absolute honor for me to teach this course, or teach this lecture actually. And currently I'm working at JP Morgan AI Research, where we have a big team doing a lot of NLP, CV, reinforcement learning, planning. We have a huge team of 70 people, a lot of people dedicated to each of these areas and doing some very, very exciting work there. So with that introduction, I could have started the lecture, but we don't have the USB-C connector yet. How's life? Very early morning lectures. Glad to see all of you come in such good numbers. And fair warning about homework 4, start early. It's, if you think you've seen or had enough of this course, you really haven't. Homework 4 is going to be taking your breath away, and sleep, and a lot of other things, mental stability, I guess. Yeah, so we'll just wait like this until the USB-C cable shows up. Any questions from the last lecture, though? I think it was attention models, which is something we're going to be talking about today as well. Oh, did you find it? Oh, thank you. I think it's pretty out there. Everybody is using it. Most of the state-of-the-art results come from, in some form, using transformers. And I'd like to start by giving you, in some sense, a preview of what transformers can do. So transformers were, as an architecture, released with the 2017 paper, Attention is All You Need. And this is a table that describes, or summarizes their results. It was a machine translation problem. And as you can see, transformer model in the last 2 rows performs slightly better than previous architectures models used to solve the problem of machine translation, both in English to French and English to German translation. So the blue scores are the higher the better. And it was able to cut training cost by a lot, like 3 orders of magnitude. So although the improvement in results wasn't huge, the training cost was cut off by a significant amount, by orders of magnitude, actually. And that's kind of what I want you to take away out of this class. By the end of it, hopefully you are able to resonate with the fact that transformers are really good at what they do, and they're also really fast. So the transformer architecture started out to be an engineering solution. And this is kind of what the architecture looks like. I mean, I found it very scary when I looked at it for the first time, spooky, and hopefully I'm able to demystify this architecture for you by the end of the lecture. Then the second landmark paper in transformers was the GPT paper. Have you guys heard of GPT? So it came out a year after that, and it did some really cool things. the GPT architecture is based on transformers and was really able to push the state of the art there. So the columns that you see here, COLA, SST2, MRPC, they are data sets corresponding to 8 different tasks. I think SST is sentiment analysis, MNLI there, the third last column is natural language inference, and so on. So they've compared the transformer architecture to the LSTM, which is at the last row. So and LSTM with auxiliary language modeling, that's close to the state of the art in 2018. And with transformers, they have a 6-point improvement. And this is not a 6-point improvement in one task. This is averaged over 8 tasks. So that is significant. 6-point improvement in one task is supposed to be significant, but when averaged over 8 different tasks, it's really big. So GPT took the world by a storm, and we keep hearing about it all the time. And the next, I think, very famous paper came out a few months after the GPT paper called BERT. People have heard about BERT here. Came out, I think, 6 months after that, and it went past GPT as well. So the first row in the table kind of shows the pre-OpenAI. OpenAI is the GPT architecture. So pre-OpenAI state of the art, which is, again, averaged over the 8 same tasks, averages to 74 points. And BERT, base and large, so base is like the architecture with fewer number of parameters, and large has larger number of parameters. So comparing BERT large with pre-OpenAI state of the art and even OpenAI GPT, it blows that out of the park as well, like 7-point improvement across 8 tasks. That is huge. And that is what transformers can do. That is why we're using transformers in almost everything in NLP these days. And a lot of vision tasks are beginning to get beginning to use transformers as well. So yeah, with that, let's get into the transformers background and see what the architecture is and what that scary diagram was built of. And before we get into the transformers architecture, I think there are 3 main ideas that you've studied before, I think. The word embeddings, encoder, decoder models, and attention. And they make up the transformer architecture. I think this is all you need, these 3 concepts, these 3 ideas to understand how the transformer architecture is built. So let's start with word embeddings. I'd like to ask this question to you guys. Can you define word embeddings? Anybody define word embeddings in your own words? What do you think word embeddings are? Yeah.
It's a way of placing different words into high-dimensional space such that the distance between them is some sort of similarity measure.
Yeah, and what does that similarity measure do?
Shows, I guess, like it's supposed to capture different language features of it.
Right, yeah, exactly. So word embeddings, and this is how I put it in my words, is a representation of words in the form of vectors in such a way that those vector representations are able to capture features of language like meaning, context, where the word is used. And yeah, it's basically showing how words are converted into vectors. And sometimes the most intuitive thing to do is use one-hot vectors. Do you guys know what one-hot vectors are? So why do you think using one-hot vectors is a bad idea? I mean, it is, I would say, not a bad idea. I mean, if you have 10 words in your vocabulary, sure. But it's a suboptimal way of representing embeddings.
Like super overfit, because then like your word is only like the exact like dimension that you match it to via one hot vector.
Can you, sorry, speak up?
So yeah, words would only really be similar if they were exactly the same. Since like the one hot vectors for 2 different words would like be completely different, they'd just be like ones in different positions.
Yeah, exactly. So man and human and rock, there are like, for example, 3 words I use. If we use a one-hot representation, man would be equally different or equally same from human as it would be from rock. So all the words are are basically as far apart or as far apart as they can be from each word, or there is no similarity, as he said. So we're not really capturing meaning and context, we're just converting words in a vector representation. And also, if we use one-hot vectors, the dimensionality of the input vector scales linearly with the number of words, unique words in a vocabulary. So, I mean, like, we have vocabularies of 20,000 words, 30,000 words. We don't want that to be the input of any kind of model. So, good to know, word embeddings. I think encoder-decoder models is something you did in the last class. So, quick recap. Encoder-decoder models in general, I think in the last class, Viksha took the example of machine translation. They formalize a task into two parts or two steps, or the architecture is divided into two parts, where the first part has the responsibility of encoding the input or maps the input into an encoded representation. So the encoder was in the last lecture in LSTM, and the last hidden state was the encoded representation of the input sequence. And the decoder, the second part of the network, does the task of generation or generating the output, uses the hidden state, final state, the representation of the input to generate the output. So I think this is something Bhiksha discussed last time. But in this simple encoder-decoder architecture, where the last hidden state is used to decode or generate, what are some limitations of such an architecture? Yeah, Rohan.
There's sort of an information bottleneck at that single link from the encoder to decoder.
Yeah. Basically, the last hidden state of the decoder has too much pressure. It has to do everything. It has to represent, find a sentence-level representation of the input, such that it has all the information that the decoder would need to generate the output. It's too much pressure. And also, sometimes this information is lost in longer sequences. And hidden states in the beginning also have useful information. So ideally, what we would want is that when we use the decoder, we also use the hidden states, initial hidden states as well, and not just a final hidden state. The problem is we don't know which ones to use, because a lot of sequence-to-sequence modeling problems, there is no there is no notion of synchrony, or not always. I mean, in the very simple problems there is, but I think in the last lecture you also saw this, that you want, especially in machine translation, for example, there is not always a notion of autosynchrony. So at the time of generation, you don't know which hidden states to look at in the encoder. So we need this magical solution at the training time to figure out what hidden states of the encoder to look at to generate new words. And that magical solution is attention. What attention does, in very layman terms, the attention mechanism is a method that dynamically gives weights or attention to different parts of the encoder or the hidden states of the encoder, or different parts of the input to make the decision. It does that automatically. So it relieves the pressure of the last hidden state of the encoder, and also looks at the previous hidden states. So instead of sending in just the final state, we're sending in all the hidden states into the attention mechanism, and that's what the decoder uses to generate the outputs. And this cyclic process, I mean, these arrows show, as we saw in the last lecture, that the decoder hidden state is also used as input to the attention mechanism. Because what hidden states we should use from the encoder, that decision should also incorporate what word we're generating in the output. And that is why the hidden states of the decoder are also used in the attention mechanism to figure out which hidden states of the encoder to focus on. So we'll slowly get into the attention mechanism for transformers. But this was like a recap of the last few lectures, or mostly the last lecture. and also the basic ideas we would need to understand the transformers architecture. So any questions up to this point? None at all. Cool. Sure? Okay, so let's get into the transformers architecture and look at the attention mechanism there, because that is really the essence of the transformer model. As the paper said, attention is all you need. So we'll look at three kinds of attention, three ways of calculating attention. Multihead attention is really what the transformer uses, but it is built from the attention and the self-attention mechanism. So make sure you stick around until multihead attention. So if you have any questions in attention or self-attention, feel free to ask them, because a bunch of self-attention modules, when put together, forms the multihead attention module. But let's start with the basic attention mechanism. It's something that Bhiksha discussed last time, but in transformers, it is used a little differently. We use the query key value formulation of attention. So so setting up the problem, we have a sequence going inside the encoder. We have hidden states of the encoder, usually an LSTM model, which is going as input to the attention module. And so H1, H2, H3 are the hidden states. This here I'm assuming my input sequence has just 3 words. Now what is the other, so at time t equal to 0 of generation, what is the other input that, so this is a question to you, what is the other input that goes into the attention module at time t equal to 0? And you've done this in the previous class. Yeah.
So you have the bottom is your input, right? So you have each one arrow for each input to the attention.
Yeah, that is true. And what is that block at the top? I mean, so you're right, like all of these 3 things go in, but like the final hidden state of the encoder, which is used to initialize the decoder, also is used to calculate attention. Yeah, I get where confusion is in some sense. So do you guys remember, like at the time of generation, the first hidden state of the decoder was the hidden state corresponding to the end of sentence symbol, and that's kind of what I mean. At time t equal to 0, the hidden state of the encoder goes in, and if we've generated the first word in the decoder, the hidden state corresponding to the first word goes into the attention module. So yeah, that is basically it. But we don't really need that information actually to understand attention. So we have 2 kinds of inputs going to the attention. One is the hidden states of the encoder, which we are in some magical way going to combine to generate the output. And the second type of input that goes in is used to find how we're going to combine the hidden states of the input. And so these are 2 kinds of hidden states that go in. All the hidden states of the encoder are called keys. The hidden state of the decoder that is used to find how we combine the keys is called the query. So is this clear? Because then we build on top of this. Yeah.
Could you explain that again?
Sorry, can you?
Could you explain that again?
Which part?
The key and query.
Okay. So it's exactly from this diagram. So is this one making sense? This is the input going in the encoder. And I think at this point, just look at it this way. The hidden states of the encoder is a representation of the input, is a higher level representation of the input. Those are called keys. And the final hidden state, in some sense, at time t equal to 0. So we're going to be using that to combine or take a linear combination of the keys, which are the inputs to the attention module or the hidden states of the encoder. That is called the value. So H3, as you will see, will change. I think I could refer to Bhiksha's slides, which you saw last time, actually. I think that will be more familiar. As soon as it opens up. Yeah, so this was last lecture. Bhiksha covered attention in the last lecture, right? So the S-1 is the final hidden state of the encoder. So this is very similar to the previous diagram. And this S-1 is used to calculate the attention and goes in the decoder. So this is what I mean by the final state of the encoder being used at time step t equal to 0 of generation, because the final state of the encoder is used as the starting point of the decoder. But that is the second source of input to the attention module. The first source of input are all these hidden states H0, H1, H2, H3. And the second source of input comes from the decoder. So right now it is S1, then S-1, then S0 goes in, then S1 goes in, and so on. So these are two sources of inputs. The hidden states of the encoder are called keys, which we want to combine. And the hidden state coming from the decoder, which changes at every time step of generation, are called queries. Does that make sense? Cool. Yeah, so basically the aim here is to show that there are two kinds of inputs to the attention mechanism. One coming from the encoder, one coming from the decoder. The one coming from the encoder are called keys, and one coming from the decoder are called queries. So now let's see how we calculate attention. Something, again, Bhiksha covered, try to keep the notation the same. We calculate attention by calculating a similarity measure between the query, which changes at each time instance of generation, and all the keys. So we take a dot product. I mean, depends on what kind of attention you use. You take a dot product between the query and each of the keys to generate the output. And this is something you're going to do in homework 4. Take dot product attentions. Yeah.
So H3 is both a query and a key.
Sorry, could you speak? I cannot understand with the mask on.
So is H3 both a query and a key?
Yes, but only at time step 0 of the generation. After that, H3 in the key is replaced by the hidden state of the decoder later on. Should I show that again? Okay. So H3, or like in this case H4, is the key as well, sorry, is the query as well and the key, but only at the first time step. At the next time step, as you see, S0 from the decoder. So is S-1 same as H4? Yeah. So at time step t equal to 0, or at the first beginning of generation, S-1 is the query, which is same as the final hidden state of the encoder. And later on, it's S0, which is the query. So that's how it changes. So the keys are fixed, and the queries change after you generate every word.
Also, the key, the query is the hidden state at the current timestamp of the decoder.
Sorry.
So the query is the hidden state of the current timestamp at the decoder.
Yeah, that is precisely correct. So I think that's a very good explanation of what he gave. The query is the current hidden state of the decoder, which at the beginning of generation is the final hidden state of the encoder, but later on it changes. Yeah, that's bang on, that's right. So to calculate attention, we take the similarity measure of the query with each of the keys, and that similarity measure could be a simple dot product or a dot product with a linear transformation, and the matrix W would contain learnable parameters. So that's how you add some learnable parameters to your attention when you're calculating attention. Now, what the similarity measure gives you is a way to assign importance to each of the keys. Then you take a softmax over all the weights, raw weights that you get to get the attention weights Wi, which now sum up to 1, basically. And then the output of the attention mechanism is a linear combination of all the hidden states weighted by the attention weights Wi. But now the hidden states are called values. So it's the same hidden states which are called keys and values. When we're taking the output, we're calling them values. How confusing is that? No, it's a real question. Anybody confused with this? Okay, that is strange. The thing is that keys are the input, but a linear transformation to the input, a generalization of the input. So sometimes we call the hidden states the keys. Sometimes you might apply a linear transformation over it and call them keys. And values are, again, a generalization of the inputs, but sometimes we might have a linear transformation over the inputs to call them values. In this case, we don't. So something like, is this visible to people at the back? So the set of values will be a linear transformation applied on the hidden states, and the set of keys will be, or like, let me put I here, but it works either way, I guess. So values and keys are a linear transformation of the inputs themselves, but they can have different ways of transforming the input. The same input and is transformed into values and keys. Now in this case, WK and WV are identity matrices. So in the example here, they're identity, but later on we'll see we'll have different matrices that do this transformation. And this is what the attention mechanism is. It is trying to find how important different inputs in the encoder is to take a decision at the current time step of generation. And yeah, that is what the attention mechanism does. Any questions here? Yeah, sorry.
What's the importance of the softmax instead of just normalizing everything?
I mean, it gives an interpretability component to your weights, how you're combining them. I guess that is the most important one. And you're also normalizing the weights so they don't shoot up, so your network doesn't blow up. Let's say, yeah, I think those two are probably the reasons why we do a softmax. Post the attention model, attention, I don't know if you've heard about interpretability of neural networks. It's attention has made neural networks a lot more interpretable, because now you can know what parts of the input each layer is focusing on. Any other questions? Yeah.
I have a question that why do we need a V and K instead of just using the H? Why do we need
It is
for
just
these variables?
It's just a generalization of the input. We don't need it here, but we will need it in a few slides. So yeah, just a preview to that. But it's basically a transformation on the input. That is it. Yeah.
In these state-of-the-art transformers, do we ever like upgrade this linear transformation into like a network of its own, or like a short, more complex transformation of it?
We don't upgrade this linear transformation, but there are like so many of these that it is a much more complicated transformation than just a linear one. So I think eventually I think what you're trying to say is like this is really straightforward. So if you use something more complicated, we might learn something better. But they have so many of these going on that I think that eventually happens anyways. Any other questions? Cool. So the self-attention mechanism. Now this is crucial to understanding transformers. Again, so right now we're not concerned about the encoder-decoder architecture. We're just looking at the encoder. What self-attention means, and kind of the name says it, in attention we were calculating the attention between the hidden states of the decoder and the encoder. In self-attention, we're calculating the attention of every hidden state with every other hidden state in the sequence. So that is self-attention. I'm calculating attention within a sequence now, not another generated between a generated sequence and the input sequence. Exactly same formalism in terms of like the nomenclature we use. Keys are the hidden states, or a generalization of the hidden states. Here they are the hidden states themselves. Keys are also the values. For each hidden state, we generate an output by taking that hidden state as the query. So in this scenario, H1 is the query, and we calculate attention with respect to that, and calculate the attention weights with respect to H1, and get the output. So we calculated the attention of H1 as the query with the remaining sequence. That is the output with respect to H1. We do it again for H2 with all the other hidden states or all the other elements in the sequence, and we do it again for H3. And that is it. That is the self-attention mechanism. It's the attention mechanism applied on a sequence, like within itself, within the tokens of the sequence itself. Is that clear? Yeah.
Ideally, self-attention should be equal to an identity matrix, because like the key would be more similar to the key itself and not the other input.
Yeah, and I guess that's why we also have learnable parameters in there. But you're right, it should be the most similar to itself and not the other ones. But we normalize it. So what you're saying is that if we're taking the dot product, it should be more similar to itself. So that dot product would be 1. But then the dot product with others would not be 0, right? It would be something between 0 and 1. And so then when we do a softmax, we're kind of normalizing this. So it is more similar to itself, but now it will also have some similarity to other words or other tokens in the sequence.
Importance of taking the self-attention, like, does it have some importance?
Yeah, I'll tell you in a few slides. Yeah. But very good question. Yeah, that's actually the entire point of the transformer paper, the importance of taking self-attention. But yeah, any other questions? Cool. And yeah, so going forward, I'll represent the self-attention block. So this entire thing, this entire process actually, as just one block called the self-attention block. And yeah, and this LSTM, in some sense, when we add a self-attention module on top of it, is what approximately the encoder in the transformer is. Approximately, not exactly. So we'll get more exact very soon. But I guess I was coming to your question. What does self-attention do here? Why do we need self-attention? And let's go through what's happening in this encoder or in this simple architecture and try and answer that question. Why do we need self-attention here, or what does self-attention do here? So this is the problem statement setup. We have 3 words, W1, W2, W3 going in. And then we have an LSTM. And the hidden states of the LSTM are H1, H2, and H3. Now, the hidden state at the first time step is just a function of the first word, right? It's just H1 of W1, because it's only seeing the first word. The hidden state at the second time step is a function of the second word and the previous hidden state, which makes it a function of the first and the second word. So all the words it has seen up till now, and so on. H3 is a function of first, second, and the third word, so all the words it has seen up till now. Now, the outputs of the self-attention block are each of them, because each of them is a linear combination of the inputs or the previous hidden states. Each of the outputs are a function of H1, H2, and H3, all of them. So does that make sense? Because that is now crucial to the answer to the question, what does self-attention do here? Cool, which means that each of these outputs are now a function of W1, W2, W3. And a question before we answer the question, why do we need self-attention here, is that in this kind of a setup, do we really need LSTM to model sequences? Because what's the LSTM doing? It's creating a contextual representation at each hidden state of more than just the input word. H2 is now a representation of the sequence it has seen up till then. So H2 is a function of word 1, word 2. H3 is a function of word 1, 2, and 3. So we're kind of creating a contextual representation of the input that it has seen up till now. If it was a bi-LSTM, all of the hidden states would be a function of all of the hidden words. So that is what the LSTM is doing to model sequences for you. Now, let's do this. Let's do this experiment. I'll replace the LSTM with a feed forward, a linear layer. Now, each H1, H2, and H3 is only a function of the word sent to itself. Now, W1, W2, W3. But because the output of the self-attention mechanism, each of the outputs are a function of all of its inputs. The outputs are a function of H1, H2, and H3, each of them. That means each of the output of the self-attention mechanism has information about the entire sequence, all of the words in the sequence. So the answer to the question, and again, what we're doing is to trying to incorporate the context, a sentence level information rather than a token level information when we use an LSTM. But now that we have self-attention, do we really need the LSTM to model sequences? No, and that's why they say attention is all you need, because attention is literally all you need to model all the words or to create a higher sentence level representation of an input sequence. You don't really need LSTM now. With all its drawbacks that you guys have studied, attention does that for us. And that is why the paper is called Attention is All You Need. And this really forms the basis of the transformer architecture. So I think, this is, at this point, do you guys have any questions? Because now we're going to ramp up and go into the transformer architecture. But this is it. If you understand this, the rest is just engineering. The rest is just putting things together. Yeah?
You can
a factor like discount in terms of parameters that attention saves you?
So attention does not necessarily save the number of parameters, but the great thing about attention is that now you're processing each word independently. The processing does not depend on the fact that the previous word has been processed or not, whereas in LSTM, that is an issue. So it reduces the training time. At this point, I don't think we're too concerned with memory in this day and age. We have big GPUs, but training time is something that it reduces, and this is what I showed in the first slide as well. It's like it really saves on training time in orders of magnitude. So I won't say it is saving on the number of parameters. I think the transform architecture in general is the biggest, and it gets biggest with every paper, with every iteration. But because we don't have a sequential, we're not understanding the sequence sequentially in some sense, we can do it all in parallel, and that saves a lot of training time. Any other questions? Yeah.
So we can't use attention for any online learning purposes. So it has to look at all the inputs, right?
Yeah. I mean, in online learning, don't you have like
Not exactly online, just online. It's like a stock prediction where you have to make one prediction per input, right? Like a sequence where you have to produce one word per one input. So in such situations, while you're processing the input, you have to produce the output, right? In such situation, can attention be used?
Yeah, I mean, like, what would be a more concrete? So you have a sequence as input, and after processing the sequence, you have to generate an output.
Yeah, that is where attention is predominantly used, or can it also be used in situations where you are giving the input, simultaneously the output is also produced?
Like a machine translation problem?
Not
No?
exactly machine translation. I'm not able to think of an example, but
Like a language modeling problem?
word tagging.
Word tagging,
Yeah.
sequence labeling. It can be used, actually. So you, instead of, so it makes, I mean, I get it why you cannot use it just looking at this, but after a few encoder layers, so you can stack these layers, and the output can be, instead of, so output can have the meaning of generating the word that you were talking about. Like sequence labeling, I think, is the problem you're talking about. So just the way that an LSTM does it. The output of an LSTM can be a word, or it can be the input to the next LSTM layer, right? Yeah. Similarly, the output of the self-attention block can be a word, or the input to the next layer, whatever it is. So that way we can do it. Cool. So let's look at what MultiHead Attention is, and now I think why we're having this distinction between queries, keys, and values will make sense. So starting again with the very same setup, we have 3 inputs going in sequence going in with 3 tokens. The keys are a linear transformation that convert the input sequence to keys. So sorry, WK is that linear transformation. WV is a linear transformation that converts the input sequence to values. And then we also have a WQ, which is a linear transformation that converts the input sequences to queries, which says values here, but that's an error. So it kind of looks something like this. All the inputs go into all of these 3 matrices that transform the input into queries, keys, and values. So now we have a sequence of queries, keys, and values, and that is used as an input to the self-attention block, which then it uses to generate the outputs. And this entire thing with a few learnable parameters now is called an attention head. So it's one attention head, or one sets of transformations between the input and queries, keys, and values is one attention head. So I'll represent this way with like H1 is the first head, which is the first triplet of these linear transformations of keys, queries, and values. Now, what transformer uses is a multi-head attention mechanism, where it stacks a few of these attention heads in parallel. So H1 would have a different set of transformations than H2, and H3 would have a different set of transformations. H4 would have a different set of transformations. So these attention heads are transforming the input in different ways and then combining them in different ways. So they're creating a more complex, a more involved contextual representation, or creating a more complex representation of the input, and that is now incorporated in the output of the multi-head attention block. So going back from here, I think we have multi-head attention, which is used in the transformer, which is composed of multiple single-head attention blocks, which is nothing but a bunch of linear combinations applied and then a self-attention block. And all of this we've studied. So now this is how they build things up from attention to self-attention to a single attention head to multi-head attention. And this is what I'll just represent by this this block there, multi-head attention block. So this is actually the encoder block of the transformer. Does that make sense? Any questions? Well, actually, I lied. This is not it. We kind of flip it. But that's it. That's absolutely right. I'm not going to change it after that. The multi-head attention block comes first, and a bunch of linear layers comes after that. But this is it. In flipped order, this is it. You get an input, and you apply multi-head attention to it, and then you pass it through a feed-forward layer. And now the function of the multi-head attention has changed. The multi-head attention is what we discussed. It is creating a representation of each token and putting it in context of the rest of the sequence. So it is basically making O1, O2, O3 a function of the entire input sequence and not just one token. And this is it. This is the encoder block of the transform architecture.
Why do we do the attention calculations before the encoding calculations?
I mean, it wouldn't matter except in the first layer. Like if you, basically what the multi-head attention is doing is combining or make the output is now a function of all the words and not just one word. So, and there are multiple such encoder blocks. So if you do it the other way around, it wouldn't matter. I think this is.
I imagine, wouldn't it be better to have word encodings rather than say like W1, W2, W3, they were one-hot vectors? Would you not want to embed them in some word embedding? And then
But they are embedded. So sorry, this is implied. W1, W2, W3 are not one-hot vectors. They are embeddings. They are a more complex representation of words. And what they do in transformers is like if that is one encoder block, they have multiple encoder blocks stacked together. So this is the multi-head attention, and this is the feed forward, and so on. So all of this forms the encoder. So you have multiple of these. So even if you had this flipped here, it wouldn't matter eventually because you would combine all the words at some point. But I think why they're doing it is the input to the feed forward layer should be, each token should be a function of the entire sequence and not just the token. So I think it makes sense to do it first before sending it to the feed forward layer. But this is it. This is the encoder block of the transformer architecture. Any questions? Yeah.
As we have new learnable parameters, do we still start with random initialization, or are there more intelligent ways of initializing? Because in the initial stages, it will just learn random.
I think it starts with random initialization. Yeah, I think so. And then let's see how this solves the machine translation problem. So because that was what the architecture was made for initially. And the transformer also has like an encoder-decoder architecture where the output that is generated by the encoder is fed in the decoder block to generate the translation. And that's kind of it. Except there's one more component called the masked multi-head attention. So remember, like initially we were taking the attention between the decoded hidden states and the encoded hidden states. So right now we're only calculating the attention in the encoder of the input, but this masked multi-head attention calculates the output, the attention on the generated output. So the T1 that was generated is now fed in, and masked multi-head attention is used. The mask term just means that it only looks at the generated output up till this point. So maybe the generated output has 5 tokens, but it will only look at the outputs that are generated up till now. So right now it's just 1, so it's just 1. And that's basically what masked multi-head attention is doing. And that's it. I mean, this is the transformer architecture. This diagram is exactly this architecture, where the first part is the encoder, and the second part is the decoder. Note that there are 2 blocks, multi-head attention and feed forward, multi-head attention, feed forward, with a bunch of normalization layers. So this is like layer normalization, similar to batch normalization, but not similar as well. And then the second part is the decoder, which has 3 blocks, masked multi-head attention, and feed forward, just like this one. And this is it. Yeah.
And they also have like residual skip connections for each.
They also have residual skip connections. They're concatenating things. Actually, a bunch of other things are going on. Like, they have multiple such encoders and decoders stacked, so it's just not one of these blocks, but multiple of them. And then there is layer normalization, which is, instead of doing normalization on a batch, you're doing it on the outputs of a single layer. And then there are positional encodings, which are giving a sequential information to the input. And yeah, I guess a few other things going on. But this is it. This is the transformer architecture, built from 3 very fundamental ideas of word embeddings, the encoder-decoder model, and attention. Yeah.
Just to confirm, what's the difference between multi-head attention and self-attention blocks?
Multi-head attention is just a bunch of self-attention blocks put in parallel. So single-head attention is basically self-attention. Multi-head attention is just these 4 things put in parallel. So that's basically it.
So how are the outputs of H2, H3, H4 be
They're concatenated. So yeah, basically they're concatenated. That's it. We'll draw it here. Yeah. So let's say we have 3 attention heads. And this generates O1, OH1. This generates OH2 at the first time step. And this generates OH3, the first time step. So the output is basically, I don't know if it's visible or not, a concatenation of OH1, OH2, OH3 into a single vector. That's basically what it is. Cool. So any other questions? This is it. This is the transformer architecture. Sure? Okay. And a quick note on what GPT and BERT is doing. So the GPT architecture is just the decoder part of the transformer. So they use the decoder part of the transformer for language modeling, and that is GPT. And BERT is like the first encoder part of the transformer. So the key difference here is the use of masked multi-head attention. GPT uses it, BERT does not. That is it. That is the difference between GPT and BERT models. So this was it. Congratulations, we got through transformers. Great job. Any questions before we move on to graph neural networks? None at all. Yeah.
Could you tell me again how you use WB, WK, and WQ? How you combine those 3 matrices?
How do we combine?
You know, how we use those 3?
Okay. I mean, it's just a matrix computation on the input. That's it. So the input is the same, H1, H2, and H3. To get the keys, we apply WK on the input to get the keys, WV on the input to get the values, and WQ to get the queries. That's it. It's very simple. It's actually as simple as it looks, just a linear matrix multiplication. That is it. All right.
How do you use K1, like K1, B1, Q1?
Oh, so that's, yeah, I think I should have had it in the slide. I'm sorry. It's the same as this formula. It's the same as this one. So maybe I'll copy it here once. Yeah, I'm sorry, I should have had this in the slide. But yeah, this is it. This is how it's used, just the way we did it before. Nice. So, yeah.
Could you repeat again on the masked multi-head attention?
Yeah, so the masked multi-head attention is used during training time when all these sequences that are to be generated are sent in, but masked multi-head attention allows it to only use, okay, so maybe I'll draw this. So let's say at training time, so this is the decoder, first of all. So when we train the model, we send in the actual sequences. So what the masked multi-head attention is doing is, like, all this is kind of happening in parallel. So to generate, and this entire block, so to generate T1 output, it should just calculate the attention up till this point. To generate T2, it should just calculate the attention up till this point. So it's basically setting the weights of, setting these weights WIs to 0 if we have not done the generation up to that point. That is kind of it. It's not too complicated. It's just setting some weights to 0 because we haven't generated it yet, and we use it because we're doing all the computation in parallel.
Do you mean that in the former lecture, when we do the sequence-to-sequence modeling, we just put T1, T2, T3 separately, once at a time, and now we put them together, and so we use the masked to separate them.
Exactly, and we're putting them sequentially because that's how we have to wait in an RNN for the previous processing to happen, but here we don't. So that we put all of them together during training, because during training is when we know what those words are.
Oh, yeah.
Not during inference. And to prevent it from using to cheat basically, to use the words it should be generating, to not use the words it should be generating, we used masked multi-head. So we basically set these weights, so the weights corresponding to these. So we set a few of them 0 basically. So we set them 0 depending on what we're generating. So if we're generating this, we'll set both of them to 0. If we're generating this, we'll just generate this, put this to 0, and so on.
So what the inputs for the inference time? So for the training, we just use the target sequence, but for the inference, what's the use?
Inference, yeah, I don't think it's required in inference. It's mostly a training time thing. I mean, at inference we have, we cannot really generate the next word before generating the previous word.
Yeah.
So it is by default happening. But in training, we're using masked multi-head explicitly.
Thank you.
I guess let's move on to graph neural networks because don't have much time. Yeah, graph neural networks. So a big jump from transformers, but they're really easy. Compared to transformers, they're literally nothing. It's a very simple architecture and might remind you of something you've studied before. Before we start with graph neural networks, I would like to show you like examples of where we use, in which scenarios we would use graph neural networks, because we already have feed-forward neural networks, CNNs, LSTM. Now we study transformers. Why do we need another set of models? And the answer to it, like the simplest answer to it is, there are a lot of scenarios where we represent data as graphs. And if we use a feed-forward network or a CNN or an LSTM, it would be a suboptimal way to model that kind of data. And that's why it's better to just use graph neural networks, which are made for a graphical representation of data. So social networks are one example where people on Facebook are friends with one another, linked to one another. Citation networks where papers cite other papers. So they're in some sense linked to other papers, and that is an information we're representing as graphs. Molecules can be represented as graphs, where the atoms are the nodes of the graph, and the edges or the bonds are the edges of the graph. Now, the molecule is different from social networks or citation networks in the way that single bonds, double bonds, triple bonds would form 3 different kinds of edges, whereas citation networks, all the edges are the same. They're just linked together. So I guess a question I want to ask is, like looking at these 3 examples of when we model data as graphs, can you come up with a general situation where you can represent data in the form of such graphs? Yeah.
When information is captured between in the relationships between 2 entities.
Exactly, yeah. So in any situation where we have data points and a relational structure between them, some relation between the data points, we can represent that scenario as graphs. And hopefully by the end of these last few minutes, you'll recognize that it is almost always true. Any kind of situation, any kind of data, you can pretty much represent as graphs. And that's why it's good to be using graphs for a few of those scenarios. So really quick introduction to graphs. Just introduce you to these 4 terms. Hopefully these are all that we'll need for this lecture. Objects or data points are nodes, are represented in a system. Data points or objects are represented as nodes or vertices, represented by V. The interaction between those data points are the relations which are represented by these arrows in the graph, or links or edges, they're called. The entire system is called a network or a graph. But actually, there is a slight difference between networks and graphs. Networks are like real-world systems, whereas graphs are like their mathematical representation. And node attributes are feature vectors of each node. So this would be something similar to like an embedding for a word, or yeah, I guess that's a fair example. So with that really fast introduction to why we should care about graphs and what certain terms are in a graph, I guess the question I want to answer here is like, what can we do with graphs? So one of the popular problems in graph neural networks is node classification. And this, an example of this is like topic classification. For example, we have each of these nodes, let's say it's a citation network, and each of these nodes represent papers. And we want to classify each paper into belonging to a particular category, like engineering, science, math, social science. So that is node classification. We're classifying each node in the graph. Then something like link prediction, which is used in recommendation systems. So Netflix uses this, models users and movies, for example, as graphs. and then based on the previous history of a user and other users, tries to predict a relationship or an edge between a user and a new movie and uses it for recommendation. And graph classification is basically to try and classify the entire graph based on all the nodes. And I think you've seen this before, graph classification, a very popular problem of image classification. It can be modeled as graph classification. So I guess the question here is, can we represent images as graphs? And let's try and answer this question, but hopefully by the end of this, you might realize that any kind of data, images, text, speech, we can pretty much represent it as graphs. So this is Bhiksha. Now we want to try and convert Bhiksha into a graph. So it's very simple. Bhiksha is right now a collection of pixels where I've drawn a few of them. And it's basically just that. It's very trivial. All the pixels have a relational structure between them that the pixels come, few pixels come after the other, few pixels come before the other, some are above, some are below. And that is it. That is the relational structure we model in graphs. So any image you can represent as a graph. So you can use graph neural networks on images as well. Similarly, any sequence you can model as a graph. So you can use graph neural networks for NLP tasks as well. And like the RGB values of each pixel is the feature vector for each node when it is represented as a graph. And that's it. You can represent almost anything in the form of a graph. So to introduce graph neural networks, I think let's try and solve a problem using graph neural networks, and hopefully we get an understanding of what they do. And we look at the problem of node classification. And the problem setup is we have a citation network. A citation network where papers are connected to other papers through the papers by what papers they cite. And we want to classify each paper into a topic of either belonging to NLP or CV. So it's a node classification problem. It's a binary classification problem. We're classifying each node into two classes. That's it. So is the problem statement clear to everyone? Everybody gets it? So let's see what we have at the time of initialization. We have a graph representing the different papers. And the nodes represent the citations, so the links between different papers. And NLP CV basically are the labels. So this is what we have at the beginning of our endeavor to classify them using graph neural networks. And another thing we have is a feature vector for each node. This can be created by any heuristic you want. One example heuristic would be the keywords. Every paper has keywords, like a few important words. We could create like a frequency thing where we select 5 words, and we create a vector representing the frequency of how often those words occur. So that is something we can do. We can basically use any heuristic, any way we want to, and generate these initialized feature vectors. The idea behind it is to capture local information about the paper or about the node in those in these vectors. Now that's the initial setup. I hope this makes sense. Now, this is like a question to you. What would you do next? This is what you have. You have a bunch of nodes, and each node has a feature vector representing the information about that node. What would you do next? Any guesses? Yeah.
Get information about nodes that are close.
Sorry?
Get information about nodes that are closer. Like, consider like
Yeah, exactly. Right now, the node, each feature vector contains local information about that node, but we haven't yet incorporated the information about the nodes it is connected to. So we want to place each node in the context of the rest of the graph, and that is why we want to somehow combine the information of the nodes it is connected to the current node. And that step is called aggregation in graph neural networks. we're trying to aggregate neighboring information into the feature vector of each node. Same as modeling relations, creating embeddings, which incorporate context in the graph. And again, a question, I guess, is how would you do aggregation or get the context of the neighboring nodes? Any guesses? Anybody? Yeah.
You have the links, so you traverse the graph and
Yeah.
go to your neighbor.
Yeah, so that tells us which nodes we want to use to aggregate the information, right? How do we aggregate it? How do we combine it?
Add together, I think.
Yeah, simplest answers are sometimes really good. That's actually what people do a lot of the times. They take the neighboring nodes. So for node A, its neighbors are B, C, and E. So you create a representation that contains information about B, C, and E, and combine it with what we know about A, which is in G, H of A. And this aggregation function should be order invariant, should not depend if we combine C, B, and E or B, C, and E. And a few examples are summation, very simple, average, taking the max. And that's how we do aggregation for all of them. So we do it for all of the nodes. And then we pass the aggregated vector. So now these are T1's temporary representations of the previous hidden nodes, but now they have the context of their neighbors. And we just pass it through a linear layer. So this is a linear layer of 4 neurons, so the output would be a 4-dimensional feature vector. And then pass everything through a linear layer, maybe have a nonlinearity in there, and that's kind of it. And this is what is called graph. This is a graph convolution network, a GCN. And then if you want to do classification, you add a classification layer on top of it, which does a binary classification, have a binary cross entropy loss, and train. And this is it. This is graph neural networks in a nutshell. So, any questions? No questions? Cool. So let's formalize this. Graph convolutional networks. One layer of GCN. What happens here is, first step is aggregation. We collect the features of all the nodes, from all the nodes, by either adding the neighboring features, taking an average summation, and then we apply a linear layer, maybe followed by a nonlinearity, depending on what you want. And you do this for every node. So do this for every node, and you have a graph convolutional network. And let's quickly compare CNNs with GCN. And so by the way, this is the definition of graph convolutional network. So I think something confusing that comes up is like, how is convolution happening here? But this is the definition of graph convolution. So it's not exactly same as the convolution that happens in CNNs. And let's see what the slight difference is. So again, we have Bhiksha. And when we apply CNNs, we take a filter, and we multiply it with every pixel in the image, right? And then we continue this. So we shift the filter to every pixel with the same weights. So a filter, when is multiplied on one pixel, has the same weights as when it is multiplied with the other pixels. And it just traverses the entire image. So this is CNN. In a GCN, what we do is the first step is we do aggregation. We combine the features of the neighboring nodes. The second step is we do matrix multiplication. So doing convolution, in some sense, is also matrix multiplication. And passing it through a linear layer is also matrix multiplication. We do that in GCNs. And we continue, so we do that at one node, and we use the same weights or the same matrix and multiply it with each of the nodes. So there is a notion of taking the same matrix and multiplying it everywhere in the graph, which is something we have in CNNs as well, where we take the same matrix and multiply it everywhere in the graph. This aggregation step is the extra step that we do in GCNs. And that's kind of the very minor difference between CNNs and GCNs. And I think that's it. So any questions on this? Yeah.
So to get influence on, like, first, do we want influence from, like, non-exact neighbors, like maybe 2 steps away from a node?
Yeah, and that's why we have multiple layers. Because in one layer, you would get only the neighbors. But when you add another layer, you do aggregation another time, which means now the neighbors have the neighboring information, so you get information about the neighbors' neighbors, and so on. So that's why you don't, and the idea of layers in GCN is different from CNNs. You can add as many layers as you want.
It's like iterations.
Right. But in GCN, after 4, 5 layers, 6 layers, you've kind of traversed the entire graph. You've reached all nodes. So you don't want to add too many layers then. Got a question?
So, after like 6 layers, like, if you have a sparse graph, like, you might not necessarily like.
Yeah, and people don't go that deep. It's like, because after 6 layers, everything is the same.
Okay.
So you probably just want 2, 3 layers in graph neural networks. Yeah.
What if you have a loop in the graph that you get in the neighbors and it goes around?
That is true. That is an issue that can occur. That is something that can happen. That is true.
Then how you handle it?
I mean, you're just you're just adding things together. So it's, yeah, so you add the neighbors together, even if it's in a cycle, and then you add neighbors. I mean, so so do you think it'll get stuck? No, it's, yeah. So you just add them up, and you don't do the cyclic thing too much. Yeah, it's simple. Hi.
Have you sent the slide to the